Good morning, everyone. Yes, it's still morning. Welcome to a SASA interest group seminar, specifically the Spatial Stats interest group. Today we have the honor of Caston, who's going to give us a talk today. Caston is a long-standing statistics community member, and he was sort of quiet for a while, and I'm so glad that I've seen him a few times now this year, and it's really exciting to have him around. And then when he volunteered for a seminar, I was like, yes, this is the way to go. So Caston holds a PhD in statistics from the University of Free State, and an MSc in operations research from the National University of Science and Technology in Zimbabwe. He is currently an associate professor in the Department of Mathematical and Computational Sciences at the University of Venda in South Africa. And he's also a member of the ISI, the International Statistical Institute, also the Institute of Forecasters, people spam phoning me, and of course the South African Statistical Association. He has also been part of ICSA. So ICSA is the Chartered Statisticians Society of South Africa. So he is currently registered as a chartered statistician since 2013. And he was also a board member of ICSA from June 2018 to Feb 2020. He is a South African National Research Foundation C3 rated researcher. If anyone's tried to go for rating, that is very impressive. So well done to Caston. His fields of expertise are time series and statistics of extremes. Caston's research interests are in predictive modeling with applications in energy and environmental systems. So this seminar is going a little bit into our other interest group, which is extreme value analysis. So we're sort of having a combined approach here. But I think obviously what Caston has to show us today is of interest for all of us that have registered to attend today. So I will hand over to Caston. I'm going to switch my camera off so that I don't use all your data. If you would like to ask a question, you're very welcome to put it in the chat, and we can then at the end answer all the questions. Thank you, Caston. Over to you.
Thank you, Inga. Good morning, colleagues. I'm going to switch off my my camera. Let me know if you are seeing my my screen.
Yeah, it looks perfect. Go ahead.
Yeah, okay. I don't need to get into details about myself. I think Inga summarized everything about myself. So my brief talk today is on modeling spatio-temporal drought risk in a changing world. A brief background about my research. My research revolves around predictive modeling. I've been working on predictive modeling since 2010 when I started my PhD studies. And my focus has been on modeling electricity demand. And of late, I've moved on to renewable energies, that's wind and also solar. But in particular, solar. I've done a bit of some work on solar. Wind, I only have one publication, but I intend to do more in this area. Lately, I have had interest in spatial predictive modeling. I've done some work on predictive modeling in general, but I've realized that spatial predictive modeling is really an interesting area, and it is the way to go as a way of extending my research interests. So what I'm going to present today, I'm not presenting it as someone who is an expert in spatial predictive modeling. I'm learning a lot in terms of spatial extremes itself. I've done univariate, multivariate extremes, but in terms of spatial extremes modeling is something that I've started recently. I've also started recently working on spatio-temporal modeling of solar energy using the Bayesian inference. I have one paper in that area, and this other one is the other paper on spatial extremes. So this is the outline of the talk. So mainly my research interests are in predictive modeling in energy systems, financial systems, and environmental systems. So although I'm into predictive modeling, my interests in applications are in quite a number of areas. So today's talk actually is going to be on environmental systems. And what I'm going to present here, it's nothing else, it's just a case study. I haven't done much of the theory in terms of spatial extremes, but I'm busy reading to try to really understand what is it that we have in spatial extremes modeling together with spatio-temporal predictive modeling using the Bayesian inference. These are two areas that I'm working on, and they're really interesting. And I've managed to identify one PhD student who will be working on spatio-temporal predictive modeling next year. But I'm still looking for a student who is going to work on spatial extremes, because what I'm going to present today is the first paper that was done by my late student who passed away at the beginning of this year. He had just started his PhD studies with me, and unfortunately, due to a short illness, he passed away. So I'm presenting this paper on behalf of the late Murendeni Nemkula. Okay, let's get into the details now. I think what we are experiencing these days is what one may want to call complex climate extremes. And what is it that is involved in this area? We are seeing a lot of heat waves, seeing a lot of floods, drought, earthquakes, and so on. So what is interesting is one would perhaps want to ask questions like, how frequently will they occur, these complex climate extremes? Want to ask, how long will they last? What area will they cover? Which is very, very important indeed, particularly if you look at floods, the cyclones, and so on. They're very catastrophic. But the frequency of occurrence of these climate extremes, as we see it these days, is in such a way that they are more frequent and more catastrophic than ever before. So it's very important that we also make a contribution in terms of modeling in this area. One of the other things we may also want to look at is how will they vary with climate? And what is the chance of getting a more extreme event? It's also very important. So these are some of the questions. The list that I have here is not exhaustive, but these are some of the questions that we need to ask ourselves as we do the modeling of complex climate extremes in some of these areas that involve extreme temperatures, heat waves, floods, droughts, cyclones, and so on and so forth. As I said earlier on, my presentation is on a case study, and this is a paper which was done jointly with the late Nemkula and my other co-authors, Chikore Hector, who is a specialist meteorologist, and Dr. Bere, who is a specialist in copula modeling. So the question we are trying to answer here is, how does deficient rainfall and extremely high temperature spatially influence drought risk? So that's the question we are trying to answer. But we are not going to get the full answer from this small case study, but it is the beginning of research in this particular area. So what we are looking at here, it's in this case study, it's an application of Mark-stable processes on modeling the spatio-temporal dependence. So we have weather and climate extremes such as heat waves, which I've already talked about, droughts and floods. We see that these days they're now more frequent and intense in several regions. And not only intense, they're also very catastrophic. They're really devastating. And we see that there is compelling evidence actually indicating that changes in climate in these extremes over time influence the living conditions of society and the surrounding environment across the globe. It is there, the evidence is there, we are seeing it. And we also need to make a contribution in this area in terms of making use of our statistical models. But one thing that we should also be perhaps looking at is we may need to start revisiting our existing statistical models, particularly in extreme value theory. Because if you look at the frequency of occurrence of these climate extremes, they're more frequent and more devastating. But if you look at the basic fundamental theory behind extreme value theory, we are looking at occurrence of observations which are rare, but when they occur, they're catastrophic. So they are rare events. But these days, these events are not rare. They're not rare at all. They're more frequent and they're more devastating. So it means there is also need for revisiting some of the existing theory in terms of the modeling. But in this case study, we are applying the existing models as they are without any modifications. So modeling rainfall and temperature extremes in continuous space is desirable as the risk at the locations where that stations can be assessed. So what we are basically interested in here is we are interested in situations where we have high temperatures which occur with low rainfall. So we have deficient rainfall, but high temperatures. And normally such conditions lead to meteorological drought. So we are very much interested in focusing on one aspect of drought, which is the meteorological drought. Sorry, I was drinking some water. So what prompted us to do this research? What motivated us to do this research? So this was our motivation. We came across this article that drought threatens millions in Southern Africa. This is the dry season in 2019. And of course, you can get the information on that website. So as a result, we thought we could perhaps begin our research in this area by looking at mark-stable processes. And the mark-stable processes, we thought we could just look at the Smith model and also the Skladda model. We did not include in this research the Brown-Rensky model. So as we can see, Southern Africa really has serious challenges. And as a result, it's important that we put our heads together so that we can assist in the modeling, and not only in the modeling, but in trying to mitigate the impacts of drought on humanity. So this is our study area, South Africa, and then it's Africa, then South Africa, and then the Limpopo province. But within the Limpopo province, we are interested in the low veld of the Limpopo province. The low veld, that's what we are interested in. So let's look at the data that we used in this study. We downloaded the data from the Royal Netherlands Meteorological Institute website. So we used gridded data. That's what we used. And the gridded data is at a resolution of 0.5 degrees. And what we have here is our study area. We only wanted a small area as a starting point. The idea was to try to reduce the complexity of the computations, because as we increase the area, the complexity also becomes a bit bigger. But in future studies, we're going to increase to a bigger area. But what we see with the precipitation data, what we see with the precipitation data here is that if you look at this region, there's some high rainfall patterns that we see. But when we move here, we find that the rainfall, this is actually for a period of 1970 to 2020. Then as we go to the east, we find that the rainfall diminishes. And as a result, it's this area that we tend to have serious problems with because of the low rainfall within this area. But the rainfall in this area, it's a bit better. But although it's a bit better, we see that it is also below the global average rainfall. Because if you look at the legend here, we find that the maximum is 482.3 millimeters. So again, it's still below the global average of about 800 millimeters. But for this period, this is what we have in terms of data on on rainfall. So as I indicated earlier on, we used gridded data. So what we do have here is each grid point would be taken as a location. So like, for instance, R1C1, it's on latitude minus 22 degrees and longitude 30 degrees, and so on. So we have got 26 grid points on different longitudes and latitudes. So from these 26 grid points, we downloaded data on precipitation and also data on temperature. So we took a sample of 6 of these stations. And plotted the rainfall. We wanted a visual inspection of the rainfall patterns within these 6 that we took. We did some stationarity tests and we found that this data was stationary. We used the sense slope test. We found that it was not significant. And then we moved on to the temperature data. The temperature data is, again, for that particular study area, which is this study area here. But one thing that we noticed with this study area, and this is really why we wanted this study area, this small study area within the Limpopo, Lowveld, the Limpopo province. If you look at this area, this year, we found that the temperature is lower than when we go further to the east. So when we go to the east, the temperature rises. And what's interesting now is if we go back, we find that the temperature is low here and the rainfall it's a bit higher compared to the other parts of the study area. And here the rainfall patterns, it's low, but temperature is higher than the other parts of the study area. So realizing that, we thought perhaps we could split our study area into clusters. So initially, we tentatively split the area into first cluster, which was from about 29.5 degrees to 30 degrees. And then the next cluster was from 30 to about 31 degrees. And then the other cluster was from 31 to about 32.5. So in other words, we had 3 clusters. By looking at the temperature map and also by using the precipitation map. But at a later stage, of course, we had to use the formal methods for clustering, which we are going to briefly talk about. So we also took 6 samples of the 24 grid points on temperature, and then we also did some time series plots. And as we can see here, there's a general, there's a trend, an upward trend, which is an increase in temperature. Oh, sorry about that. For all these 6 here, meaning that temperature over the years has been increasing. That's what we are seeing here. And that's a very important observation at a later stage. So having done looked at the study area, talked briefly about the data, and the objective, of course, is to model drought risk using rainfall data and temperature data. Then the next thing was then to look at the modeling process. So we did data pre-processing, exploratory data analysis, which is the usual stuff that is done. Then the next thing was to look at hierarchical clustering. We'll briefly talk about this in greater detail at a later stage. Then, of course, when you are working with spatial extremes, you need to transform your data, whether you transform it to the Gumbel margins, the Frechet margins, it's all up to you. But we transformed our data to the Frechet margins. We see this a lot in literature, and the Frechet margins seems to be more flexible than the other margins. And then after that, after transforming, then we fit the max stable models. And in this case, as I indicated earlier on, we fitted the Smith model and the Skladda model. We didn't use the Brown-Rensky model, although we know it's a more flexible model. We wanted to start with these simple standard models. So of course, the Smith model is based on the Gaussian covariance function, and the Sclater model, some of the covariance functions are the Wilton-Martin, power exponential Cauchy, and generalized Cauchy. And of course, the next thing was then to do some goodness of fit tests and then model selection. And then lastly, we estimated the extremal coefficients. So what we then did in this is that we used precipitation data on its own for our estimation of extremal coefficients. We also used temperature data on its own. We did not do the joint modeling. It is the next part that will be looking at in our future research. Actually, we have started working on that, on the joint modeling. I think I'll briefly talk about that right at the end. So this paper was meant to be an introductory paper to have an understanding of the extremal coefficients. In other words, the dependence of rainfall within these grid points. Grid point number 1 and grid point number 2. What is the dependence structure like? And later on, then we can look at the joint modeling of the two variables. So because of that, we decided then to look at precipitation data on its own, temperature data on its own. But as I've already said earlier on, in terms of the maps that we saw, we thought perhaps we could use 3 clusters, but then we used the formal methods for clustering. And when we look at clustering, you can use your k-means, you can use your partitioning around medoids, you can use hierarchical clustering. But because we are using max-stable processes, we cannot use the k-means algorithm because it's based on averages. And there's a problem of if you average the max-stable processes, you won't get a max-stable process. That's the problem with the k-means algorithm. So you cannot use it here. But the partitioning around medoids can be used. But we decided to use the hierarchical clustering based on the agglomerative method. But in terms of determining the optimal number of clusters, we used the k-medoids or partitioning around medoids. And this was used using the gap statistic and silhouette statistic. And for both, we got the optimal clusters to be 2. But we went on to use 3 based on what we had seen on the 2 maps for precipitation and temperature. So we finally, after some serious discussions in the research group, we then decided that we should go for 3 clusters and not 2, which we got from the gap statistic and the silhouette statistic, which was done using PEM, partitioning around medoids. But one thing we also need to note here is that when you do clustering, the very first thing that you need to do is to see whether your data is clusterable or not. So the cluster structure of the data is very important. So this was done prior to clustering. This was done using the Hopkins statistic. And the Hopkins statistic is based on the fact that if the statistic is greater than 0.5, then that data is clusterable. If it's not, then it means it's not clusterable. You may go on to do your clustering, but there are problems because the clustering is in such a way that it does not form a good clustering structure. So for the precipitation data, the Hopkins statistic was 0.7, and for the temperature data, we found it to be 0.8. So both the data sets were found to be highly clusterable. So these are the 3 clusters for precipitation, and these are the 3 clusters for temperature. So let's have a brief look at the max-stable processes. As I've already said earlier on, we looked at the Smith model and also the Sclater model. We left out the Brown-Rensky model, but this will be considered in future research. So briefly, max-stable processes are an extension of univariate extreme value theory as we are familiar with in continuous space and with the dependency. So max-stable processes model the spatial dependence of extreme values, which is very important. Unlike the univariate case, here we are looking at different locations, different points scattered in a region, and you are interested in the dependency of those points which are scattered in space. And those points, you've got data, you've got some variable that you of interest that you want to study, like temperature, like rainfall, in this case. So a max-stable process denoted by Z dot is the limit process of maxima of independent and identically distributed random fields, yi, x, and x in RD. So in short, what we are saying is that if we've got, say, two locations, location 1 and location 2, from each location, you've got, for instance, precipitation data over that period, 1970 to 2020. In the other location, you also have got data. So the X here represents our locations, is the set of locations, X1 and X2. So our X is in D. And in this case, if you look at two locations, it means your D is equal to 2. And if you're only dealing with the D equal to 2, it makes life very easy. But otherwise, we are going to look at 26 locations or grid points. But of course, dealing with all of them makes the computations really, really difficult. The complexity of the problem really increases. That's why we decided then to split into clusters so that we have got smaller dimensions. And of course, the concept behind the max-stable processes is also based on asymptotic theory, like the univariate case. So if you've got two normalizing constants, a nx and bnx, then it follows that zx is found to be the limit of the maximum of your random fields minus the bnx over anx, of course, x in RD. So that's how the max-stable process is defined in a nutshell. But the max-stable processes are based on the concept of extreme value theory. So the univariate generalized extreme value distribution then plays a very important role in modeling max-stable processes. So the univariate marginals of max-stable processes belong to the generalized extreme value family, which we are all familiar with. That's the generalized extreme value theory, which is the shape parameter, psi, the mean, and then of course the scale parameter sigma. So normally the marginals are transformed, and when they are transformed, this helps us to fit the max-stable processes. So there are quite a number of transformations that can be used for the marginals. You can use the Gumbel if you want. You can use the Frechet, and in this case we use the Frechet. There's the Laplace marginals, but in this case we use the Frechet marginal transformation. The Frechet marginal transformation is very flexible transformation compared to the other transformations, and the model after transforming is very straightforward. That means you're looking at a case where your shape parameter actually is 1. So this makes it very flexible and robust. Briefly on the Smith model, the very first model that was developed in terms of spatial extremes modeling, or max-stable processes, it was proposed by Smith in 1990, whom we know to be one of the greatest scholars in the field of extreme value theory. But later on, this was extended to the Skladda model in 2002, and of course, the Brown-Rensky model also came in a little bit later, trying to bring in the flexibility in terms of the modeling. So the initial study in this area was done by Smith. So the Smith model actually is a very simple one, a very simple model, and it's got a closed form representation of the extremal dependent structure. Because it's got a closed form, it makes even the computations very simple, very easy. But one of the greatest challenges that it has is that it only uses one covariance function, which is the Gaussian covariance function. That's the main problem. And the other problem that it also has is that it's very good for modeling, say, environmental data, which exhibits asymptotic independence. It is very good at that. It's not as flexible as the other two types of models, the Sclater model and the Brown-Rensky model. So the Smith model is the one that we have in equation 4. I'm not going to get into details with that. Then the other model that I talked about is the Sclater model. The Sclater model brings in flexibility in terms of the modeling, unlike the Smith model. And it can also model different types of dependency and even different types of marginal distributions. The Smith model is very good when your margins are transformed to the Gumbel margins. But the Smith model, the Sclater model is more flexible. You can actually use any marginal distributions, Frechet margins, Gumbel margins. Is very flexible, just like the Brown-Rensky. It's even more flexible than the Sclater model. And of course, this was proposed by Sclater around the year 2002, and that's the simple model for the Sclater. That's the Sclater processes or Sclater model. The flexibility also comes in as a result of the use of the different types of covariance functions. So these are some of the covariance functions that used, which is the powered exponential, Wheaton-Martin, Cauchy, generalized Cauchy, and so on. Now, in this study, as I said earlier on, we are interested if you've got two locations, for instance, location 1 and location 2, and you're looking at precipitation data, you are interested with the dependence at the tails of the distributions of the precipitation data on these two locations. That's what we are interested in. And what we are interested in is the positive dependence. That's what we are interested in, which means the upper tail. In this case, that's what we are interested in. We're interested in the upper tail. So there is a way of measuring this dependency from Mark-stable processes. And this is done through what is known as the extremal coefficient. So if we've got two locations, Z1 and Z2, then the extremal coefficient functions for Mark-stable models can be derived directly from their bivariate distribution. So what we have here are two extremal coefficients for the Smith and the Sclater model. So the one for the Smith, actually, as I said earlier on, this is based on the Gaussian covariance function, as we can see. And again, this is one of the greatest limitations because we are assuming that everything is Gaussian, which may not be the case. But the Sclater model, which is the next one, is based on rho, where rho is your correlation function between the 2 points, which is x1 and x2. So the extremal coefficient then is very important because it helps us to understand the extremal dependency of the variable of interest in two locations, or it could be two variables of interest, maybe at two different locations. But in this case, we are treating each variable independent of the other variable. So it is precipitation at different locations, temperature at different locations. Then, of course, there is an element that comes in of distance measure. That is the next thing. We talk about the extremal coefficient, but it is linked to distance measure. And the distance measure in spatial extreme value theory is based on what is referred to as the madogram, which is nothing else but is your L1 distance. So there's a relationship between the extremal coefficient and the distance between the two locations, say location 1 and location 2. So that's what we are looking at. So the extremal coefficient, which is denoted whether you're using the Smith model or you're using the Sclater model, between two locations x1 and x2, is dependent on this VF, which we refer to as the F madogram. So the F madogram is nothing else, it's your L1 distance, which in spatial statistics is the semi-variogram or the symbol madogram. So this is the relationship between the two. And of course, the other one is just for how we estimate the madogram. So the madogram here can be estimated as your L1 distance. So it's nothing else, it's simply representing your L1 distance for the madogram. But we are estimating it from the sample data. So the formula we have here is for estimating it from the sample data. So the distance becomes important. And secondly, the dependency at the tails of the distributions of this particular variable on station 1 and station 2 is what we are interested in. So let's look at our preliminary results. And this is on precipitation, and this is cluster 1. And our data was already transformed to the Frechet margins. So what we see here is the relationship between the distance and our extremal coefficient. That's what we are looking at. So if we go back to this here, the extremal coefficient in equation 6, the extremal coefficient, we find that it's in the interval 1 to 2. When it's 1, it's perfect dependence. And when it's 2, that's your perfect independence. So the extremal coefficient it's analogous to your correlation coefficient in a way, in a sense, except that for this we are interested with variables which are on two different locations. That's what we are interested in. So the dependence, and also looking at the dependence at the tails of that particular variable. This is where the difference is with the symbol correlation. So looking at these preliminary results that we got, we find that as distance increases, that's your H, as it increases, we find that the dependence becomes weaker and weaker and weaker. In other words, we're heading towards independence. So this was also of interest to us because we were saying, let's look at the topographical features of this particular area and see how it is like. And we noticed that there are a few mountains in that particular area, and that perhaps could be one of the reasons that we see that as distance increases, we find that the rainfall also is going to decrease. So in other words, the dependency between location 1 and say location 2, we find that it is going to be weaker and weaker as the distance increases. But of course, we were then interested in looking at the full structure of the dependency. This was done, and we found out that for points which are very close to each other, the dependency is very high. But as we move further away, the dependency also becomes weaker and weaker. Oh, sorry about that. So this is a summary of all the 3 clusters. The first one that we saw was for cluster 1. So for cluster 2 and 3, we find that the distance here that we see is data that was already transformed. That's why the distance is in it's not in any units. But as distance increases, we find that the extremal dependency here it's also increasing. For cluster 2, this is what we got, and for cluster 3, again, this is what we got. So we did the same thing with temperature. But for temperature, it was a different story altogether. So for cluster 1, for instance, we find that as distance increases, the dependency is still very strong. It is still very strong, despite the fact that, of course, it's getting weaker and weaker, but it's stronger than when we compare it to that of precipitation. And then we also had a summary of all the 3 clusters. So as we can see, the dependency is still very strong as distance increases. The same applies for cluster 2 and then cluster 3. So in conclusion, this study is an introduction to a project where spatial dependence is non-stationary and modeled on a large geographical scale. What we also noticed from this study is that human activity interaction is needed to reduce the potential impacts of compound precipitation and temperature extremes. But in actual fact, we need an in-depth understanding and analysis of the physical processes leading to the compound extremes in a given area. So this was really meant to be an introductory study to have an understanding of the dependency of precipitation on different grid points or different locations, an understanding of dependency of temperature on different points on this particular study area. That was the whole idea behind this small study. So it was a very small study, a very simple study, but this study has led us to then move on to this particular area now that we want to then focus on. So the first paper that we wrote there, it was like an exploratory, like what we do in exploratory data analysis. But our focus is in this region 4, where we find that temperature is rising, but at the same time, we find that rainfall precipitation is very low. So what we have just done here is to do the classification in terms of clusters. So for cluster 1, for cluster 2, and also for cluster 3. We are in all those 3 clusters, we are interested in region 4. And what is it that we want to do in those regions? We want to estimate the joint probabilities of rainfall and precipitation for these 4 classifications: mild drought, moderate drought, severe drought, and extreme drought. We may, of course, also look at conditional probabilities, but we think that joint probabilities will give us more information compared to the joint probabilities. Because the problem with the joint probabilities here would be we are fixing the temperature and then we want to see what happens when rainfall decreases. But it's something that we may also want to look at. So in short, this is what I thought I should share with you. It's very basic. It's very, it's an introduction to the study in this area. And as I've indicated earlier on, I've just started working in this area. I found a lot of interest in this area, but I thought I could not just read without perhaps publishing a small paper. So normally when I do research, I read a bit, publish a paper, read a bit, publish it, until I'm really confident in that particular area. Thank you very much.
Thank you, Caston. That was lovely. And I love how you ended there, that if you just read until you've mastered it. I think that's just general great advice for all our researchers on the call. Excellent. Any questions for Caston? Very interesting. Normally.
Thank you very much, Prof, for a very interesting presentation. I take note that you have emphasized the fact that this is still an introductory study, but just one question from my side. You've shown a time series plot, and then also one of the observations you've indicated that temperature over the years has been increasing. Have you perhaps tried to find out or just to understand what were the reasons behind the increase of temperature over the years? Thank you.
Thank you, Namli. Thank you for the question. Yeah, indeed. we've seen a trend with those 6 grid points that we took from the study area. We have not really delved into the analysis of what contributes to the increase in temperature. But let me answer you in this way. It's something that we need to study, of course, in greater detail. But let me answer you this way. We suspect that this is due to climate change. Climate change is playing a significant role in this. You know, these greenhouse gas emissions. And I mean, it's evident, like I indicated, we are seeing this, it's happening. These cyclones, we are seeing them, they are happening. The temperatures, remember the 2015, 2016 temperatures in South Africa, it was really bad. Not only in 2015, 2016, even now we are experiencing this, the floods that we're experiencing. So we think the increase is as a result of climate change. Of course, we need more studies in that area. So we didn't identify the cause. Let me put it that way.
It's a big question. Anybody else have some questions? Comments? Maybe while people are thinking. Caston, I think this is really interesting. So Ansi and I see Ansi's not here, I know she's got classes. We're looking at some hail modeling, also extreme value. And I must say that when you were starting and you were talking about you chose that area because it was manageable computationally, that was very valid. So we also started and we wanted to do the whole of South Africa, and then we realized, oh yeah, that's not going to work. It's far too computational. And I think this is very interesting for statisticians because it's a huge data problem and it's got huge dependency, as you said, in time. And you've got 3 things there. You've got space, time, and then your extremal values, your distributions. How are they also related to that? So it's really, really interesting. Lots and lots of work to do. And the other thing that I found very interesting, and I think you went on in the same direction as us, is we realized that you've got to, because it's so complex and so much dependency, you've first got to do your exploratory analysis, but it's not a traditional statistical exploratory analysis. It's a spatial, it's a temporal, it's in the extremes and that sort of thing. And I think that's already very challenging with this sort of data. So, so maybe I can phrase that as a question. What do you think? Do you think we have enough structure on how to do a proper exploratory analysis for spatial temporal data? Or we just sort of winging it as we go?
I'm not very sure, as I indicated earlier on. I started actually last year working on spatial predictive modeling. So as I indicated, like in our case, what we did, it was first to try to understand the data itself and also try to see if we can put it into clusters, because using 26 grid points and then we do the computations, it's computationally expensive. So in terms of the structure for spatial extremes, is something that is that I still really need to read. There's still a lot in terms of the theory that I need to master. But as I indicated, normally when we read, we find something interesting. We just want to put it on the public domain. Although it's exploratory, but we have it on the public domain, and then we continue to go deeper and deeper. But the truth of the matter is that this is a very interesting area, and I think my personal opinion about this is the way to go in terms of modeling, in terms of forecasting. Spatial predictive modeling is the way to go, even in my area of energy. This is the way to go.
Because it's related.
Yeah, this is the way to go.
Yeah, absolutely. That's and I think also that we're there. We have a unique, in terms of the South African context, there's a unique research opportunity there that's not in the rest of the world. And I think there's no one really doing this. So it's a lovely research direction to go into here in South Africa. Anybody have any other questions or comments? Okay, Doesn't
Maybe
look like
it was too simple. Everything was
no,
just
no,
exploratory.
no. I thought it was lovely. All the new. I made notes on. Because I don't know anything about extremes. So and I do very little temporal modeling as well. So it was really interesting. Thank you. I'm sure as they think and if they come have a research question, they'll remember you and then send you some emails. Okay, so we still have 2 more seminars for our SASA spatial statistics interest group. We have one next Tuesday at 5 o'clock, so that might be a little bit easier for maybe people are working, maybe in the middle of the day is a bit difficult. And that will be a sort of a geostatistical lecture by Dr. David Rose from Wits University. And then we have another one on the 8th of November at midday at 12 from Dr. Sebnen from UCT, who's got some spatial traffic modeling. So I think very interesting things that we've got coming. Normally, I see your hands up. Was it gone? No? Okay. The old hand. Okay. Thank you, Caston. I'll give you a last thanks. I really, really appreciate your
just
effort.
a comment.
Yes, normally.
Oh, yes,
No.
thanks, Prof. I think my network is a bit delayed. It's an old hand. It was just a comment to say Prof will really like to see some work on the spatial predictive model in future, looking at energy. I think that would be quite interesting. So it's
Absolutely.
a challenge to you, Prof.
There we go, Caston. We're waiting for you. As soon as you have your next paper, you come straight back in and give us another talk, please.
Actually, there's one paper that was done by my PhD student who graduated this year. That paper is already out. It was also like introductory type of work on solar.
Oh, okay.
Yeah,
all right.
But we used the eight radiometric stations, and then we did split the training into initially 5, and then later 3 stations for testing. But I think it's going to be a talk for another day.
Yes.
Again, that is exploratory because what we did there, we realized that there is a lot that needs to be done in that particular area. But next year, I already have identified one PhD student who is going to work on spatial-temporal predictive modeling of wind energy. I think we're going to use the wind atlas data, and it's more reliable than the data that we get from radiometric stations. Exactly. Most of them, they don't keep. Thank you, Inga. Your radiometric station there is a very good one. The data is clean, and but quite a number that we've seen, they are giving us problems. And we may end up also using satellite data, like what we did for rainfall. Yeah. But one thing I need to point out, perhaps, is the use of grid data. Why we use grid data here? You'd find that meteorological stations, there are very few. So when you do your modeling, you won't be able to capture some of the salient features of the other areas. So it's like there's hidden information elsewhere because of the radiometric stations which are scattered. But if you use grid points, you tend to get more information to have a better understanding of whatever that you are doing.
Absolutely, yeah. And this is what makes spatial modeling so interesting, because a lot of the remote sensing data, as you say, is the lattice data, your image data, and then you'll have point data and how you want to try and put these data sets together and help them talk to each other, and that makes it really complicated, but interesting. Okay, so Caston's basically volunteered. Next year sometime he'll come to us another seminar on on either wind or the solar stuff. We really appreciate your time today, Caston, and thank you everyone for also joining the seminar and taking some time to come and listen to Caston. And hopefully we see you again on Tuesday evening at 5 o'clock. Otherwise, maybe on the 8th of November. Otherwise, hopefully at the SASA conference later in November. Thank you, everybody. Have a lovely day. Thank you, Caston. Appreciate your time.
Thank you so much. Have a good day. Bye.
Bye.